We've all heard it before, right? Trading is just gambling, an utterly outrageous statement from people who have no understanding of what probability and statistics, not just in the lab, in academia, but in practice looks like. In this video, I'm going to prove to you mathematically that if you consider trading to be gambling, then you also have to consider buying gas for your car, buying groceries, and anything similar to also be gambling. To understand why this is the case, we're going to look at random variables. We'll look at stochastic processes. We'll understand this idea of probabilistic, statistical, and distribution convergence. We'll move out of the classroom then into the real world. We'll look at this idea of uncertainty and what actual gambling looks like relative to a game of incomplete information. Then we'll actually take a look at this idea of buying groceries and trading. In any case, whether we're dealing with a random or an uncertain system, nobody can predict what the outcome of any one event will be. It's never safe to bet your entire portfolio value on just one event. That's not how the trading space works. The only event that is safe to bet your entire portfolio on every single time is access to my Jupyter Notebooks. This Jupyter Notebook will be linked in the description below. I will also post it to the Quant Guild library on GitHub, where you can find all of my Jupyter Notebooks and associated YouTube videos, along with all of the source code for my quant builds. At the top of this Jupyter Notebook, you'll notice some related Quant Guild videos applying probability and statistics to finance and trading. This idea of time series analysis, retail versus institutional trading, trading versus investing, this idea of accumulating expected value over time, quant versus discretionary trading, and of course, busting 3 popular trading myths that these trading gurus love to propagate. If you're unfamiliar with any of these ideas, I highly recommend that you check these videos out first before tackling one like this. Moreover, these videos certainly take a lot of effort to create, so if you'd like to help support the channel so I can continue to create videos just like this one, please like, comment, subscribe, share. It helps me out tremendously. It is always greatly appreciated. And if you'd like to master your quantitative skills, check out quantguild.com. Maybe you come from a background in business, economics, computer science, and aren't too sure where to get started on your quant journey. Maybe you're an aspiring quant or a working professional looking to sharpen your quantitative skills. In any case, Quant Guild is for you. This is the platform that I wish I had when I was studying to become a quant. We have over 90 quant lessons in math, probability, finance, an adaptive practice engine that scales with your skill level so you can progress to more and more difficult topics with gamified rank-based progress, interview questions with fully worked solutions, trading games, courses from A to Z in coding, math, probability, statistics, and more on the way. And you can get started right now for free. So if you'd like to help support the channel and master your quantitative skills, check out quantguild.com. Without further ado, let's get started by discussing this idea of a random and an uncertain system. This is going to allow us to bridge the gap between theory and practice. We can see exactly where things start to break down and where all of the misconceptions and misinterpretations come from. We're going to start with this idea of a random variable and a stochastic process. All a random variable is a set of possible outcomes with associated probabilities or likelihoods of those specific events occurring. So what I have here is a random variable x. This is going to represent a dice roll. This is a discrete uniform random variable. We can define a random variable in terms of either its probability, mass, or density function, its distribution function, or its characteristic function. That is effectively just the derivative and integral or the Fourier transform of any of those objects. Once we have the definition, then we can effectively see the probability or likelihood of different events. We can draw then from that distribution. So this brings us to the idea of a population versus an empirical distribution. What I have on the left here is the population distribution of a dice roll. Everything has the same probability of occurring, 1 through 6. And on the right here, what I'm going to do is I'm going to roll a couple of die and I'm going to record the results. And what you see on the right is a sample. It doesn't perfectly reflect the population distribution, and that's because every sample is effectively random. We don't know what the outcome of any one dice roll is going to be, but what we record on the right here will eventually look like the probability mass function, that is this population distribution, so long as we have enough dice rolls. That is a very important idea to understand. This is a small sample. If we increase the sample size, then eventually these blue bars will look like these green bars. But that's only the case in theory, in the lab. When we move on to the real world, we'll see when we model things as random events, that will not be the case. Probabilities then, in the random system sense, literally represent a frequency of outcomes. In other words, if I was to roll a dice 1,000 times, on average, 1/6 of the time, I would see a 6. Then 1/6 of the time, I would see 5, 4, 3, and so on and so forth. That is the interpretation of probability that we use in the context of random variables. This is also why we know that the distribution, the empirical distribution, will eventually converge to the population or the theoretical distribution. That is given to us by the law of large numbers. This is the idea of statistical convergence. All random variables have associated statistics, a mean, a variance, skewness, kurtosis, higher order moments. We can generate those with a moment generating function, or we can apply analytical formula outright. In any case, the law of large numbers is effectively telling us if we look at the statistics associated with the empirical distribution, they will converge to the population value. What does that actually look like? Well, if I roll a large number of dice, then eventually the mean is going to converge to the theoretical value of 3.5. That is not by accident. That is given to us by the law of large numbers. It's ensuring statistical convergence. Now, if the mean converges, then so will the variance, so will the skewness, and so will the kurtosis. They're all functions of a mean. So if they are finite and the mean converges, as we see in this particular example, then all of the other statistics will converge as well. Now that's great, but what does that have to do with probabilities and distributions, right? We're talking about convergence of these sample statistics to their population value. That's effectively what we see here. This horizontal line is at 3.5. That is the population mean value. And the cumulative mean, the cumulative empirical mean, is converging to that population value. But that says nothing of the distribution. That says something about the statistics of the distribution, the mean, the variance, the skewness, the kurtosis. How do we know that the empirical distribution and probabilities associated with it will converge to the population distribution? Well, that's also given by the law of large numbers. And that's because we can represent any event outcome as a Bernoulli random variable. A Bernoulli random variable is just a binary random variable. You can think of like a coin flip, 0 or 1, they're independent trials. And the expected value, the mean of a Bernoulli random variable, is just a probability. And if the mean converges, and the mean is a probability, then that means the probability converges. And that's what we're seeing here. We're saying effectively, if we continue to sample from this population distribution, eventually the empirical distribution will converge to the population one, not just the distribution itself, but also probabilities associated with different events drawn from that population. That is an absolutely critical idea, especially in the context of Monte Carlo simulation. If there's some sort of complicated composite event that you're trying to find the probability of, you can just simulate it, and then you can find an approximate probability for that outcome by this construction. That is the law of large numbers. Geez, Roman, convergence, the law of large numbers, what's the point? Well, the point is, if you understand these mathematical and statistical objects, you can use them to inform your decision making in randomness to accumulate wealth. And I have a market making example of this for you here. What we're going to do is we're going to make a market on a dice roll. Effectively, what that means is I'm going to allow people to buy or sell at a certain price. I'm going to quote a bid offer, and then the realization, so the outcome of my dice roll, will dictate P&L. So for example, if I sell to somebody at 1 and the outcome is then 6, they make $5. All right. Now, what do I know about a dice roll? Well, each outcome itself is random, but based on what we saw above here, I know that the mean value is 3.5. I also know that the empirical mean will converge with probabilistic certainty to that theoretical value. So, what can I do? Well, I can apply this knowledge here and use it to quote a bid offer. So what I'm going to do is I'm going to put that theoretical mean value in the center, and I am going to quote a spread around it. And effectively, every time I engage in a transaction, I am going to be up for an opportunity to collect that edge. Every single trade will allow me then to accumulate that edge over time. So what do? I quote a bid offer. I'm going to effectively have 4 and 2 here. So somebody can buy at 4, they can sell at 2. That is my dice market. Now, if I run the statistics, then what's going to happen? Well, I can apply the formula here for expected value or mean, and I can see that the mean is what? It's 0.5. So I have a positive edge per trade. What do we know? Well, the law of large numbers will ensure that each empirical outcome will eventually converge then to this theoretical one. And if I run this simulation for you here, this is going to be a simulation of the dice market that we are making. I'm going to have people arrive, they're going to buy, they're going to sell, and you can see I'm going to generate a whole bunch of wealth paths if I was to quote this bid offer. And what you see here is I don't get to choose which sample path I walk. Everything is effectively still random. Remember, we're saying that in the long run, if I continue to draw from the same distribution, everything will converge to what? That theoretical path value. And that's what you're seeing here is the empirical paths are converging to, they're tracking that theoretical path. And over time, I'm going to continue to accumulate wealth. That is exactly the purpose of these random variables and these statistics. I know for certain that if I continue to make this market, I will statistically continue to generate wealth over a series of trades. A few important considerations for you. Just because you have an edge, it doesn't mean that you are going to automatically be making money in every case. You can see that our sample path here that we walked actually went negative at one point. In the long run, we will accumulate wealth. But in the short run, you can still blow out. It's a very important concept. Moreover, this is not a remark on ergodicity, the time versus ensemble average. I have a video dedicated to this topic in the context of optimal bet sizing, additive versus multiplicative bets. I'll leave a link to it in the description below if you're interested in that topic. Again, this is not a course or a lesson on stochastic processes. This is simply an application of probability and statistics. Now, lastly, probably one of the more important ideas here is that this convergence is only guaranteed in a random system. In other words, the dice roll is not going to change over time. That's what we talked about up here with the idea of the empirical convergence and the statistical and probabilistic convergence. This market that we're making isn't going to change. That right there is what ensures our theoretical profitability in the long run. This is not the case in reality. This is where most of the confusion comes from for both students and professionals in this space. When we go about applying these models in practice, we use the same constructs. We still have distributions, we still have statistics and probabilities, but we no longer have this idea of convergence. And that's because unlike with a dice roll where everything is fixed, we can keep rolling the dice, it's not going to change. Things change over time. And this is where the idea of non-stationarity starts to come into play. This is what we would call an uncertain system. I'll play for you this animation here. And what you'll see is the difference between the two. On the left, I'm effectively observing the same thing I observed in the market making example above, right? For that dice market, we have this theoretical expected value line. I don't get to choose the sample path that I walk, but they're all tracking that theoretical line, and that's because there's convergence. But on the right here, what do we see? We see a whole bunch of crazy sample paths, and there is no convergence at all. Some do very well, some do very poor, and that's because the overall expected value of the process is changing, and it's going to change over time, and it's never going to converge. You can think of this roughly in the context of stock returns as the idea that what? Nvidia is an entirely different company now than it was in what? Early 2000s? Moreover, the entire environment was different. The macro environment, the administration, so on and so forth. There is no convergence, and that's because the population distribution, the data generating distribution, is always changing. And that is a big problem for our quant models. And that is also why these probability statistics and distributions do not converge. And it's also why we can't just have a fixed trading strategy. That is not how the space functions. There is no one golden goose trading strategy that will indefinitely print money. The space is dynamic, it's constantly changing. That is effectively why everybody still has a job. Knowing now the difference between a random system and probabilistic, statistical, and distribution convergence, and an uncertain system, the lack thereof, we can talk about this idea of gambling, what it actually is, the idea of a game of chance versus a game of incomplete information. Now, in any case, we will never be able to predict the outcome of one event. That is never our goal. Our goal is instead to figure out if we can act with positive expected value. The expected value in any of these systems is going to dictate the trajectory of our wealth path. So again, I don't know what the outcome is going to be in any case, but if I'm acting with positive expected value, just as I was in that market making example above, we will accumulate that wealth over time. That's this idea of accumulating expected value, EV or edge. If we're acting with negative expected value, then we will be losing money over time. The question you should be asking yourself now is, what dictates then our expected value? That is going to be either the system itself that we are interacting with or our actions. This brings us to the idea of a policy function. A policy function is a collection of actions that we can take based on our current state in efforts to maximize our expected value. What does this actually look like? I'm going to show you two examples here. I have a nice animation for you. I will play both an optimal policy function and a suboptimal policy function. What you will find is, in this case, I'm acting with an optimal set of actions that influences my expected value trajectory in the positive direction. Again, I don't get to dictate which sample path I walk, but over time, I will accumulate that edge. I will be generating wealth. If I act suboptimally, as I do in this bottom chart, you will see that I accumulate losses over time. That set of actions is dynamic. It is time variant. This is not a trading strategy. This is not one simple set of steps. This is a series of actions. I can go long, short, any instrument I choose. I could trade options. I could trade futures. I could trade options on futures. This isn't just one input output. This is a collection of actions that I can choose to make informed decisions in the face of uncertainty and maximize my expected value. Sounds abstract? It is. This is a very high dimensional space. This itself is an abstraction. On the left, what I'm showing you here is what? The expected value per play. This function itself has concavity. That is to say, it's very easy to always act with what? Negative EV, negative edge, negative expected value. Just because it is very difficult to find this optimal policy function, it does not mean that the entire space in itself is gambling. That is the main purpose of this chart. Our actions may or may not influence our expected value in some sort of system. That set of actions is dictated by our policy function. Let's give a concrete example of a policy function. We already have one in our market making example. Our policy is to quote what? 2 at 4? That's how we made our market for the dice roll. And that is an example of a policy function. But is it the optimal policy function? Well, no. Because really what we're doing is we're acting somewhere above this x-axis here, but we're not at the optimal policy. We can quote an even more aggressive spread, and we can have a stronger expected value. But what's going to happen if we quote a really wide spread? Are we going to have anybody transacting with us? No, and that's really hard to account for functionally. So this entire space, hopefully you're starting to get the idea, is about acting optimally, but choosing a series of actions, not necessarily in a fixed capacity, but in a time variant capacity, to enable the accumulation of this edge. It is not a fixed space. If you go on Interactive Brokers and you look at the bid offer for Apple, is it fixed? No, it's changing literally every single second. That is how markets are made. Things change over time. We're dealing with this non-stationarity. This is where all of the pieces of the puzzle start to fit together. Understanding now that our actions are dictated by some sort of policy function, and that policy function can effectively influence our expected value, we can talk about this idea of a game of chance and what gambling actually is. Gambling occurs anytime that you willfully and unnecessarily engage with a system that has a fixed negative edge against you. This is not an uncertain system. There is statistical convergence. We are operating with a random system. Some examples: roulette, slots, lottery tickets, craps, all of those have statistical convergence. You are guaranteed, if you continue to engage with that system, to lose all of your money regardless of the actions that you take. Now, if we take a look at an example of what this looks like, we have two charts. One on the left, where we have an unconditional expected value, and one on the right, where we have a conditional expected value, and we're acting optimally. It doesn't matter in either case. If we choose an optimal set of actions or a suboptimal set of actions, we will statistically eventually lose all of our money. Mathematically, what does this look like? The unconditional expected value is equivalent to the conditional expected value, even if we have this magical pi star function that is our optimal policy. That is what it means to gamble. You are basing your wealth path trajectory solely on luck. If you want to argue for idiosyncratic instances like martingale roulette, you can. That's banned at pretty much every single casino. The point here is there is nothing that you can do to influence the trajectory of your wealth path. Games of incomplete information are fundamentally different. Your policy function dictates the trajectory of your wealth path and how much wealth you accumulate over time. Crucially, in these systems, we don't observe convergence. We don't have this notion of the law of large numbers. So unlike with the case of gambling, where there is statistical convergence, you are guaranteed to lose all of your money if you continue to engage with that system. In the case of a game of incomplete information, everything changes over time, including that optimal policy function. Some examples of this include the idea of election betting, sports betting, poker trading, and grocery shopping. Okay, more specifically, the unconditional expectation or the conditional on a random action is not equivalent to the expectation conditional on our policy function, whether it be optimal or suboptimal. In other words, our actions influence the trajectory of our wealth path, unlike in a game of chance, otherwise known as gambling. What I have here is a chart to illustrate this. On the left, we have an ineffective policy function. We're accumulating losses. But on the right, we have an effective policy function, and we are accumulating edge, accumulating expected value, or this wealth over time. Some crucial considerations for you here. Acting with an optimal policy function or even an effective policy function may be easy or difficult depending on the system that you are engaging with. But the complexity of your policy function outright and its time variance does not make the system or the game of incomplete information gambling outright. There is no fixed negative edge against you. your decisions, optimal or suboptimal, directly influence your wealth path. I can always raise a huge hand in poker and fold. I can always trade an indefinite number of times to accumulate an absurd amount of transaction costs. I can always buy things at the grocery store that I do not need. I can buy a tank of gas and dump it all out. I can act suboptimally in all of those systems. In fact, there is a stochastic or uncertain component to grocery shopping and buying a tank of gas as well. When you leave your house, you do not know what the price of the food that you're going to buy or the price of gas at the gas station is going to be outright. That is the market price. That's the spot price effectively. It's the same idea if you go on the exchange and you look at the Apple stock, you know what the price is. That's the spot price. You don't know what it's going to be next week. You don't know if you would have been better off waiting. Maybe there's going to be a coupon. Maybe there's a discount. That is precisely the point that I'm trying to make here. Just because in some cases it's easier to act optimally than it is in other cases, it doesn't make the entire system gambling. Let's look at our wealth path buying groceries with a simple policy function. What I have here is a policy function. I am going to effectively buy the only things that I need from the store at the lowest price possible. That is my policy function, and I am going to attempt to accumulate this positive expected value, that is the cumulative savings, as I continue to engage with transactions at the grocery store. What you're going to see on the left here is the grocery cost function. I'm trying to get as low as possible on this theoretical cost function every single trip to the store that I make. And the lower I get, the more theoretical savings that I will accumulate. What you're going to observe here is I'm going to be darting around the cost function. That's because what I end up actually buying is going to be a combination of where I go, the discounts that are running that day, and all of the other available stores, whether it's online, that I could have purchased those goods at. And what you're going to see on the right here is you're going to see a series of sample paths. And what I want you to focus on now is this purple dashed line. That is now the theoretical expected value. What do you notice? It itself is stochastic. It is random. Effectively, when we find this pi star function, and I defined it above here as the argmax of the expected value, this optimal policy function is not maximizing the value of the path outright. It's maximizing the expected value. If I act with the optimal policy function, it would have yielded this path here. It's not just going to yield the absolute best path outright. Again, we can't choose the path we walk. We're trying to maximize or optimize for expected value. We want to be correct on average. That's how we accumulate wealth. We act with positive EV. We make small incremental bets, small incremental decisions, and accumulate that edge over time. We don't know what the outcome of any one of these trips is going to be. Are we going to be saving a whole bunch of money this trip, or are we overpaying? We don't know. We will never know that outright. The same way we will never know the outcome of one trade. Instead, we're trying to act optimally. So what I'm going to do is I'm going to instill this policy function. And in this case, it's fixed. But maybe it shouldn't be fixed. Maybe it should be time variant. They're running a deal now, right? So I'm not just going to buy the minimum amount that I need. I'm going to buy more. That'll allow me to save more on future trips. That is the perfect example of a time variant policy function in this framework. And this exact same logic applies to suboptimal actions and trading. Critically, again, here, there is no convergence, right? This entire system is a game of incomplete information. Our policy function is going to dictate our wealth path trajectory, and that is necessarily going to change over time, which is what makes the space so elusive. So I ask you this simple question now: is grocery shopping gambling? I can always act suboptimally, can't I? I can always just accumulate a massive amount of spend on things I don't need. I can waste money. I can always do this. That's very easy. I can come up with a terrible policy function and I can lose a ton of money. And I can do that trading. I can do that in poker. I could do that sports betting, election betting. But really, at the end of the day, Your policy function dictates the wealth path trajectory. There is no fixed negative edge against you. You're not gambling. You're making poor decisions in the face of uncertainty, fundamentally missing the purpose of this idea of accumulating positive expected value over time. Moving to the trading space, we observe the same lack of convergence, right? When we have a random system, we have the law of large numbers, statistics, probabilities, distributions converge. When it comes to uncertain systems, games of incomplete information, we don't have that luxury. Unlike, of course, in the case of gambling, where things do converge and there's a negative fixed edge against you. When we're looking at the trading space now, we think of a policy function and the associated wealth path trajectory. What you can see here is we're not going to want to fix a policy function. You can see sometimes, certainly it's optimal. Sometimes it's positive EV. Other times it's net zero EV or even negative. And you can see the consequence in our wealth paths on the right side here. We're accumulating edge on some trades. On others, it's net zero or even negative EV. And you can see consequently in our wealth path that it's just effectively flat. We can't just fix our policy function. We can't come up with some sort of set of actions, an optimal set of actions today that will for certain work 1 year from now. That's not how this space functions. We need to constantly and iteratively revisit our models, update our assumptions to make optimal decisions in the face of uncertainty to accumulate that expected value. That is not gambling. There is no fixed edge against you. And if you consider this to be gambling, then you would also have to consider grocery shopping to be gambling. Too long didn't watch. Here's your executive summary. Random variables define a set of possible outcomes with accompanying probabilities and likelihoods. By the law of large numbers, probabilities, statistics, and distributions converge. We tend to model uncertain systems or events, non-stationary events or processes, with random variables or models that use them functionally, even though in practice, these quantities lack convergence. This leads to a lot of confusion about the efficacy of statistics in the real world for both students and professionals alike. The purpose of models isn't to perfectly replicate what we're observing in the real world, but rather to aid in making informed decision making in the face of uncertainty. Games of chance and games of incomplete information are examples of systems that both impact our wealth over a series of plays or time. In either case, we never know what the outcome of any one event is. The expected value of the system is going to dictate the overall trajectory of our wealth path. And sometimes our actions dictated by a policy function may influence the trajectory of our wealth path. In a game of chance, it does not. That is where gambling comes from and all of the negative connotations, rightfully so. If we engage willfully in a game of chance with a fixed negative edge against us, there's nothing we can do statistically. We will lose all of our money. The only optimal action to take is to not engage with that system versus a game of incomplete information where our actions, our optimal actions, can influence the trajectory of our wealth path over time. Just because there is difficulty in optimizing that policy function, that set of actions that will influence our wealth path, it does not make that system gambling. It is a game of incomplete information. We can make optimal choices to adjust the wealth path trajectory if we're going shopping for gas or groceries, trading, playing poker, sports betting, so on and so forth. We can always accumulate an infinite sum of transaction costs. We can buy things we don't need. We can be wasteful. Just because you can act suboptimally, it doesn't mean the entire space is gambling. That is the purpose of this video. Some future topics, technical videos, and other discussions to look forward to. This idea of advanced Markov chains, breaking out the iPad, pretty much a lecture in stochastic processes class. This idea of geometric Brownian motion, we've already talked about standard Brownian motion and the affine transformation, that arithmetic process. I'd like to extend to this multiplicative process and then get into the Black-Scholes partial differential equation. We could talk about the analytical and numerical solution, and then we can start to extend into this idea of the Greeks and operating an automated delta neutral trading system with interactive brokers. I'll leave a link to interactive brokers in the description if you'd like to get started. I use them for all of my quant builds. I'd also like to do this video on Kalman filters and non-stationarity. We talked about that in this video. An uncertain system is dealing with this issue of non-stationarity. It's a big problem in quant modeling. There are things we can do to model exogenous factors that could impact the mean of some sort of process that we're analyzing. And I discussed that in my video on time series analysis. I'll leave a link to it in the description below if you would like to check out that topic. I'd also like to maybe do more qualitative videos, most popular quant models for informed trading, buy-side versus sell-side quants. I've toyed with this idea of a quant roadmap. Let me know in the comments below what you'd like to see next. That's going to do it for this video on proving that trading is not gambling with math. I hope you enjoyed. I hope you learned something. This video certainly took a lot of effort to create, so if you enjoyed it and you'd like to see more like it in the future, please like, comment, subscribe, share. Again, it helps me out tremendously. It is always greatly appreciated. Check out quantguild.com to master your quantitative skills. Other than that, thank you so much for watching, and I will see you in the next video.